Hey everybody, my hair looks crazy. Oh my gosh, gotta get the hair right. Good morning, Noel. Good to see you there. Good morning. I'm sorry, I know this is supposed to be a review session mode. Is it possible to work on some chapter 17 or chapter 14 quiz? We can. Sorry, a tiny bit under the weather today, so hence I'm doing everything online. There will not be in-person office hours today. Good to see you, Kaolin. Christopher, and I also ate a coconut nature zone and nature valley. And I always cough when I eat coconut, so doubly here. Don't eat coconut when you got a slight cough, which is gonna sound worse than you already are. So do some chapter 14. We can. We're gonna also be doing more review. Let me pull up my Pearson. I'm tearing up from all the coconut. Let's throw out right here 1,000 points. How's everyone doing? I'm just gonna cough into my shoulder. Try to mute, but just started Sunday. Started feeling a little under the weather. So I'm going to lock myself in my office today. Woke up this morning, was hoping I've got a last lecture tonight. Not my last lecture, but you know what those are. And so I was hoping to be 100% to do it. And I started to walk around this morning. I was like, I'm a little coffee. I'm a little, not the good kind of coffee way. Not the kind of coffee that we want. What should we do? Should we do the homework? Noel right there? I know Brian is mushy. Brian, improved new homework experience coming November 6th. Thank you, Matt Pearson. Brian is mushy. What does that mean? I don't even know what that means. Let's do, I'd like the homework as well. Let's do the homework. A lot of people want the homework. Let's knock it out. Because I see some people have done the homework. Some people haven't. Brian is mushy. Don't be mushy. October 28th, the homework's due tonight. Oh my gosh. Okay. Let's do the homework. Let's see how to do the homework. Yes, please the quiz. We can do the quiz too. We'll do some homework and quiz, and then we also have I'm going to be streaming again later today, which is kind of good. So the fact that I'm sick means I get to stream, not be in person. Try to limit exposure around people. So we try to do here. Brian can't read the screen. 5:33. Okay, here we go. Stat 201, chapter 14. Homework. Let's do the full homework. Let's do it. Okay, here we are with the homework. Let's do the homework, then the quiz. Thank you so much, Noel. I'm feeling like 80%, but I don't like being around people if I'm sick, because I'm like, as best we can limit exposure to people if we are not doing well. It's one of my policies of if you're sick, try to not be around people. Once again, I'm 80% right now. I'm feeling good, but then little. So sick, the exam got to be moved. No, not that sick. I'm here on campus, but locked away in my office. So don't come in my office. Okay, let's check out this one right here. Now, here's the thing. For this chapter, you've got a sleeping Morty right there. So you wake up the Morty and you say, okay, Morty, here's what we got to do. We need to know for this chapter the conditions. We need to know the notation. We need to know the formulas. How about so sick? No, Kaolin. No, Kaolin. Not that sick. I'm doing fine. Just sick enough where people don't got to be around me. I gave a guy an elbow bump today. He said, Brian. I said, hey. I gave him an elbow bump. So let's look at this first one right here. Now, the first step we do whenever working on a chapter 13-14 problem is to figure out if it's categorical or quantitative. They are looking at the weights of salmon. So is that categorical or quantitative? The weights of salmon. You have to think, when you weigh a salmon, are you getting a yes, no answer or a quantity of weight? It's quantitative. So what you'd want to do now, if you're working on problems like this, especially the test, is you immediately go to the test and not the topics. You go to the formula sheet, and on the formula sheet, you go down, excuse me. Sorry if anyone's hearing me clear my throat throughout this and all that good jazz. You go right here and you take only the data on the means. So these are the formulas you would use, and this is how you would do it if you're on the exam. Notice how it literally says the standard deviation of y bar. I'm not blocking any important stuff right now. That's a z-score for it. We're not going to use that right now. It says it wants the standard deviation of y bar. That's this right here. And once again, you also know this because we're doing quantitative data, and that's when you deal with the mean. The standard deviation is 3. That might be the original standard deviation. The original standard deviation for my company is 3. Now, what is that in notation? The original standard deviation. No, you're on the right track, Christopher. Christopher, illustrate some points. So what is that in notation? Christopher, you're on the right track. You're on the right track, Christopher. Keep going. You're not cooked. You got to lock in. Lock in to not get cooked. Cook the exam. Don't get cooked. What is 3 in notation? In notation, 3 is what? Aiden, good to see you here. What is 3 in notation? You'd be shocked how easy this question is once you see it. It's all about knowing the notation. This question is a huge know the notation. We've got the formula. So what is 3 in notation? It's sigma. Great job, Noel, right there. That's the true standard deviation, the original standard deviation of the population. Now we do it for each sample size. So now we have a box of 4, a box of 49, and a thing of 121. Now what's interesting about each of these is that they're all perfect squares. So if you take 3 right here, which is sigma, divide by square root of 4, 3 divided by square root of 49, and 3 divided by square root of 121. So once again, all of these are perfect squares, so you're going to get, for each one of these respectively, 3 over 2, which is 1/2, 3 over 7, which is 3/7 is 0.1 or 0.43, something like that. No, yeah, we'll figure it out. We'll type it in the calculator. And then 3/11, which is, I think, 303030. Around that, it's pretty interesting what you get when you do 3/11. It's not going to be 303. It's going to be 2727. Oh, it deals with ninth, so it's a repeating ninth. So really fun with that, because 9 and 11, interesting stuff. And then 3/7, I'm thinking 0.43. It is 0.43. Should have known the 0.27, 0.27. Got to memorize my fractions. Can't for the life of me remember the names of the symbols. Sigma. And just do this to remember symbols. Sit down and try writing them out and write down mu, sigma, P, heart. That was weird. P right there. It's like an autocomplete on my computer. So sigma is the true standard deviation. Mu is the true mean. P is the true proportion. Then you can turn them into their respective sample versions of y bar, the sample mean, s, the sample standard deviation, and p hat, the sample proportion. Once again, chapter 10 has some of the notes on this, so check out chapter 10 and try writing them down, repeating them, flashcarding them. Best way to do it, just say them, put them on your screen or something. Sigma, mu, proportion. Christopher's getting it down right there. You're practicing. Yep. And so now we're going to enter in these values. So we basically solved the first one. What is the new standard deviation for a sample size, a box of 4? That's going to be 1.5. You divide the original standard deviation of 3 by square root of 4. The new one right here is going to be the 0.43 because it's the original standard deviation of 3 divided by square root of 49, which is 7, 3/7 right there. And then the last one is the 0.27 because it's the original standard deviation of 3 divided by the square root of 121, which is 11. 3/11 is 0.2727. Now, this goes into the conditions right here. So which of these would be best shown by a normal distribution? We have what is called the central limit theorem. This might be... Yes, exactly. That is correct. So the central limit theorem states that the distribution of the mean will become more normal. You notice right here it says distribution of means of sample size 5. Well, if we have a skewed distribution and we take sample sizes of 2, you can see here's the middle right there. Notice how I can go and be like, right there's between those. And if you keep doing this, you'll get another distribution, but a distribution of means. And the central limit theorem states that the distribution of means will always be more water and more water. This distribution of means will have 2 characteristics about it. It'll have the same center. There's the same center because mu y bar equals mu. And if I do the simulation more, there it is right there. There's the same center. Same center on this, but it'll have 2 things. Once again, we're making sure we understand the concepts by doing this homework. The 2 things that the new distribution of the means will have is that it'll be more water and more water. The central limit theorem states 2 things that will happen to the distribution of the means. The distribution of the means will become more and more. You could see it as I increase n. This is 25 observations averaged together. My left eye says no to looking today. So there's 25 observations, the mean of 25 observations, and then the repeated doing of it. More normal and tighter, kind of thinner, tighter. tighter. Yeah, kind of thinner. Tighter. Because we're dividing the original standard deviation by the square root of the sample size. So this 6.22 right here, if we take 6.22 and divide by the square root of 25, we get 1.24. And you say, Brian, that's 1.25. I say, law of large numbers. There you go. Oh, really? You're going to do that to me? It's right on the cusp of 1.25. So law of large numbers states that if we continue to do repeated trials, it'll approach the truth. And so we can law of large numbers this through large repeated trials, which is a chapter 10 concept. No, chapter 12. Chapter 10 is sampling. The numbers don't matter.
It doesn't matter!
So it's going to be the larger one, the palettes, because that allows for the large enough n to kick in. And regardless of the underlying distribution, the sample distribution of the means approaches the normal as sample size increases. So let me check this one, because as long as they're like, nope, regardless, it doesn't matter if the distribution is normal or not to begin with. As you can see right here, we don't need a normal distribution. Regardless, that means no matter what the underlying distribution is, the central limit theorem states that with large enough n, the distribution of means will be nearly normal. So that's the large enough n condition for checking. And you should know your three conditions: random, 10%, and large enough n for quantitative. Random, 10% is success failure for categorical. What would you expect the sampling distribution of the mean scores, class scores to be for each organization? Well, this goes back to the formulas. Look at your formulas right here. What would you expect the mean to be? Don't look at their answers. So what they're talking about... Oh, is this a different question? I think we went to the next question, right? Oh, it is. It is. So with this question right here, I was like, scores. Don't read their answers. Do not read their answers. What formula, when it says, what would you expect the sampling distribution of means scores to be close to? What would you expect the mean to be close to? Does anyone know the formula for this? Well, don't we have mu y bar equals mu? So maybe we should find what in this question? What should we find in this question? Because we have mu y bar equals mu. Let me put question 1 in here. Question 1. Yeah, let's go find mu. So what's mu? Now, so y bar is a sample mean. Good answers, Aiden, right here. What we're looking for is we're looking for this concept right here, which is one thing, and then the answer we are looking for is mu, which is this. So mu y bar is a concept of the expected sample mean. That's how mu y bar is read, and good answers, Aiden, right there. It's not like mu times y bar. A lot of people think that, like mu times y bar. Y bar is a theoretical sample mean we could get when sampling. So mu y bar equals mu, and then also if we get a large enough sample size, what should the shape of this be? With a large enough sample size, what should the shape of this be? So if you get a large enough sample size, what would the shape of it be? Don't read their answers. Normal. Because if we get a large enough sample size, which we've sampled classes of 25, that's probably large enough that such that the distribution will be normal. And that's your large enough n condition. So the distribution for the larger organization will be approximately normal. That makes sense. We're doing 2. We have a 9. So we have 2 different n's right here. N of those. So those are n right there. And the sample size for the small organization is too small. That's possible. The distribution for the smaller, no. As n, good to see you, Braden. As n gets larger, the distribution gets more normal and tighter. Once again, let's show the central limit theorem applet. So answer A looks the best so far. But remember, if we have a smaller n, it's going to be less normal and tighter. And larger n, right there, this is the larger n, more normal and tighter. So it looks like answer A is going to be your best. Both distributions will be approximately normal. Does it say the original distribution is normal? Oh. So here's the thing. Wow, that was weird. The original data is normal. Basically, Christopher, right there. So this is how large enough n works. Is you have to look at the original shape, and they told me that the original shape is unimodal symmetric. So the question states in the blue box I just made that the data is really the data is unimodal symmetric, which means it looks like this. So now for a sample size of about 9, that's about 9, the distribution of means will look like this. For a sample size of 25, which is the larger class, it'll look like this. Notice it's tighter. But since the original data is normal, the new mean distribution will be normal. So I was originally thinking it was A, but since both distributions were normal to begin with, well, the distributions of means will also be normal. The large enough n condition states you must first check the shape of the original distribution. The more skewed it is, the larger n needs to be. So let me ask you this. Will the sample size of 2 have means that are a distribution of means that is normal? Type yes or no in the chat. If I take 2 observations, will the distributions of means of sample size 2 be nearly normal? Yes or no in the chat. This is the large enough n condition. You'd have to look at the original shape, and then you have to know the sample size to go with it. You are correct, no. It'll still be skewed. It's too low. So what we would need a sample size of about what, Noel? Notice how it still has this right skew? So if it's skewed, you need a sample size of at least what? So the more skewed it is, the larger n needs to be. And if it's skewed, you need a sample size of at least 25. 1, 25, and 100. Check out last class for review. And there it is. And it might actually be more heavily skewed. You know, still got a little bit of skew right there. So we might. Don't touch my shoulder. It's still got a little bit of skew, so maybe we need an even larger n. How about down below here? Will the sample size of 2 make a distribution that is nearly normal? Yes or no? You have to look at the original shape of the data. Will the sample size of 2 make a distribution that's nearly normal? Yes or no? Will the sample size of 2 make a distribution that's nearly normal? Yes or no? Will the sample size of 2? The answer is yes. Why? What is the shape of the original data? What is the shape of the original data? The original data is normal. So since the original data is normal, anything we do with distributions of means will also be normal. Remember, the more skewed it is, the larger n needs to be. So if we have something that's not heavily skewed, a sample size of 2 won't do. Sample size of 2 will still lead to a skewed distribution down below. 25 is large enough, such that the distribution of means is nearly normal. But if we have something that's extremely skewed, if it's extremely skewed, then we might still have skew and we need a 100. So if it starts normal, the sample size doesn't matter. That is true. Because remember, the new distribution of means will just be more normal and tighter. So if it's already normal, so if it's skewed, we need either, not either. If it's skewed, you would need what? Good question, Braden, right there. So the ways I describe things are normal, skewed, very skewed. The metrics are 1, 25, 100. So if it's skewed, you need a sample size of what? Christopher's starting to understand. If it's skewed, you need a sample size of at least what for the central limit theorem to kick in and the distribution of means to be nearly normal? You need 25. If it's very skewed, which is even more skewed, you need an even larger n, so you need a sample size of what? Because the more skewed it is, the larger n needs to be for the central limit theorem to start to normalize the data even more. So you need 100. Christopher on fire right there. And if it's normal, you only need a sample size of this because it's already normal, hence, as Noel said. So if it's normal, you only need a sample size of what? Because if it's normal, it's already normal, so it doesn't matter. You only need a sample size of what? 2 works. Technically 1, because the original data is normal. That's a sample of 1. That's a sample of 2. So the original data is, right, you could do it with 2. So it doesn't matter because it's already normal to begin with. And the whole point of these conditions, once again, teaching to the test moments, is to see if we can use the normal techniques. So the whole point of these conditions is to do normal stuff. Right here, we have a mean score of this is this many standard deviations above or below the mean. So we're going to do 169. Okay. We got to do some mathy stuff. Let's do math. I have no temperature and I'm COVID negative, but my right nostril is, I can't breathe from it. Sometimes. Sorry about that. We have mu y bar equals mu. Standard deviation of the sample mean equals to sigma over square root of n. The standard deviation is equal to 11. Is it for both classes? I think for both classes. So 11 divided by square root of 9 for 1, and 11 divided by square root of 25, perfect squares. So 11 over 3 and 11 over 5. Does that make sense, respectively, the large and the small class? Does everyone see this? You have the small class and the large class, and they differ in their sample sizes. Sample size, respectively, for the small class is 9 students, and sample size for the large class is 25, hence these numbers down here for the small and the large. They both have the same standard deviation, apparently, so same standard deviations were plugged into the formula, just differing in their respective sample sizes right there. So make sure to plug in sigma over square root of n for each one. 11 is the standard deviation. Yes, exactly. Thank you so much. Good answers, Christopher, right there. 11 is right here given in the question as the standard deviation of the distribution. The mean of the data as proposed is right here. And so we are given mu. So now we need to go into the formulas now that we have this, and mu was 150. What was it? 158. And that is just what we expect to see in these classes. So it asks, is 169 odd? 169 in notation is a y bar. So now we do y bar minus mu over standard deviation of y bar. We're going to do it for both class right here, because it's saying is a sample mean of this odd. So we'll go small and large, and the y bar over sigma over standard deviation of y bar is equal to, so y bar is 169, which is the observed, minus the top of the equation is the same. The only thing that differs about these are the standard deviations, 11 thirds and 11 fifths. You could multiply right here. The difference up top is 11. Oh, that's beautiful. 11 over 11 thirds. That's going to be equal to 3, right? And 11 over 11 fifths, that's equal to 5. So it's 3 and 5. That's beautiful. Man, they give us a good question. With the S and L clashing, are they in a fraction as well? Oh, it's just my notation. Hopefully, this is for the small class standard deviation. This is for the large class standard deviation. So you could write, is this making sense right here, Christopher? Tell me if I've worked too fast or done problems right here. Where did 158 and 119 come from? Oh, sorry. My bad handwriting right here. 169 is the, oh, there you go. 169 is going to be the, I'm trying to find a good color. Y bar. Caleb, thank you for asking. Yeah, I'm glad I'm doing this online. 158 is the true mean, and the standard deviation is found via these formulas, but make sure to take the proper respective standard deviation. So we went and found the standard deviations right there. Does that make sense, Kaylin? 158 was given in the question, or do we find that? 158 was given at the top. Yep. Here's 158 all the way up here. Yep. So this is mu, and this is sigma. This is n sub large. This is n sub small. So there we go right there. So it really boils down to notation. So you can see down here, I'll put it next to it. So this equation right here is, this would be sigma over n sub small, sigma over n sub large. Right here. Does that make sense? Yeah, no, don't worry, Christopher. Keep asking. This is what office hours are for. It's a lot of work. It's a lot of work. It's plugging in. So I've color coded a little bit, standard deviation. Thank you so much. Keep asking those questions. It's a lot of work. It's a lot of seeing what you got, keeping it straight. And I understand it's very tricky, but plug into the formulas. And once again, these formulas are given right here. We'll show the formula sheet again. All your formulas are right here along the bottom. You know, so we're using sigma over square root of n. We're using mu y bar equals mu. And then here's the standard deviation, or the z-score formula. We just used y bar minus mu over standard deviation. So you can see the formula is right down here. So it's just observation minus mean over standard deviation. It's how many standard deviations is the observation away. So it's just knowing how to read them. So this is the smaller class. They were 3. Wait. And is, oh, in the larger class. It is more likely that the smaller class, because they have a smaller, there we go. It's more likely, now we having the S and the L answers, those are used below and above. Exactly. Mm-hmm. And 152 is how far below the mean? How far is 152 below the mean? You can see where the mean is at. How far is 152 below the mean? Just look at this right here and just tell me. 152 is how far below the mean? Just look at the mean right here and look at 152. It's 6. So you know what that means? We can do this problem a lot quicker if we go to our worksheet and we just go back here to the end of this where we were solving this right here. And we just replug into the top of this, and we just take the distance of -6. Does that make sense right there? So we just plug in -6 and solve the following way. So you can times by the top, or you can do algebra right here. This is just algebraing it out. So it'd be -30. Is that right? I think it is. No, wait. Oh my gosh. Yeah, it is right. Okay, over 11. All we did was plug in the distance it is above or below. Can you explain how we can tell if it's going to be smaller or larger? So the small class has a sample size of 9. Thank you, right there, Christopher. Small class has a sample size of 9. Large class has a sample size of 25. So as we plug in the formulas, we just use the small and the large. Does that make sense, Noel, right there? Let me know. -18 over 11. So we just plugged in the -6. It's 6 below. And you could go back through here and just put 152. So I'll show it. I'll write it out. You'd go here and write 152. 152. And that would be the y bar. It's not color for y bar. So the next one said y bar is now equal to 152, and it wants us to figure out which one is odd there. How's it looking? How's it looking? Christopher, I'm glad this is making more sense. -18 over 11. These are going to be weird fractions. So the small class is, we can do 18 over 11. And it does say below, so we just copy paste in. And then we delete down. And then the other one was 30 over 11. And it does say below, so they're not having you do the negative, which is kind of weird. And there we go. That should be right. And the small class is closer because their z-score is closer to it. So the small class was closer. It's going to show me it again. Small class, I think, is always closer. So, but z-score being smaller means closer. How do we figure out what equation to use in the mean section? Maybe this next one will help us highlight that. Good question, Christopher. Yes, how do you know which of the one to the right is even, which even number is bigger? How do we know which one is the right one? Just kind of notation right here. Big thing, keeping your notation straight on it, where we have, thank you, Noel, for asking, is we have the small sample size of 9 and the large sample size of 25. Then when you go down here and solve, you have the small, which uses 11 over 3, because that's the equation right there. And you have the large, which uses 11 over 5, because that's the equation right there. So keeping it straight is the goal. So for the smaller or larger, the small uses 11 over square root of 9. The larger uses 11 over square root of 25. Yeah, and I'll be doing it probably later again today. It's the big thing is keeping all of your numbers straight, all the numbers straight. It's a lot of math, a lot of formulas. We'll do the next one right here, and we'll see how we do. Let me undo the show answer. Okay. This one is, I think this is the easier version of it. I really like the one where we work it out. As you can tell, there's a lot of steps to these. We'll do another one right here. Okay. So what do you think we need to do before we work this question? Mark your what? Before working this question, mark your what? The practice is, and identify if it's means or quantitative or categorical. Before working the question, mark your notation.
Notation, brother.
You got to do that. You got to mark your notation. You have to know what's what. Mean is what? Mean is what? Standard deviation is what? Mark, nice job right there, Christopher. So what's what? It says a mean of this. It says it's slightly skewed. So it's slightly skewed to the right, so it's got a shape like that. Slightly right skew. What does mean in standard deviation? So a waiter believes their tip is this. So what is the notation? What is mean? What is standard deviation? What are they? What is it, man? Mu and kind of ST, we won't write ST, we'll write mu and sigma. Mu and sigma. Which one would be the mu and just number plug into it? So then if you want to know what mu y bar is, you already have found it, it's mu. So you already know if it were to ask you what is the expected mean, it would be mu, because mu y bar, the expected mean is mu. So anyway, you can't determine that the party tips him at least 20, a singular party. The original data is right skew. So we can't use the central limit theorem yet. The distribution is skewed, meaning it's not symmetric and does not meet the conditions for normal. So the probabilities of values cannot be determined because it is skewed, as it says right there. So we can't use the empirical rule yet. So because it's skewed, we can't use the empirical rule. Data states it's skewed. Can you estimate the probability that 4 parties will tip 15? Well, with the central limit theorem, do you think 4 is large enough? If it's skewed, do you think a sample size of 4 is large enough? I know it may look this way. Do you think 4 is large enough? So mean is mu, right? If it's true mean, like he believes this as a fact, not from a sample, that'd be y bar. Sample mean is y bar. True mean is mu. So this is probably not large enough for the central limit theorem to kick in. Look, it even says large enough. It literally is talking about large enough n, large enough sample size. A sample size of 4, n, is not large enough for the central limit theorem to kick in. How about 10 parties? This is where maybe it's starting to kick in. A sample of 10 parties is large enough. It probably is large enough. A sample size of 10 parties is large enough to use the normal model. Maybe. I agree. It's probably starting to approach. So what would be the mean for a sample size of 10? He believes he makes $9.60 on average. So what would be the mean for a sample size of 10? What would be the mean for a sample size of 10? It's probably what we said next would be 25. Yeah, it's iffy on this one because 25 is what we would want. This question's all rightish. It does illustrate as n gets bigger, it gets more normal. What would be the mean for a sample size of 10? So we know mu y bar equals mu. So given a sample size of 10, the mean would be what? What would be the mean? For a sample size of 10, the mean would be what? Don't look at their answers. Mu y bar equals mu. So if we have a sample size of 10, what would be the mean? There's mu. So mu y bar equals mu. Yeah, it'd still be this. We'd expect, yeah. Now, what's the standard deviation for a sample size of 10? What's the standard deviation for a sample size of 10? Be careful. What's the standard deviation for a sample size of 10? Not 5.4 still. That's where you get caught. So good answers, brain right there. We throw some points. Not 5.4. What is the new standard deviation for something? We can solve it out right here, but it's 1 something. And So the new standard deviation. There we go. Standard deviation. Probably it's gonna be the right answer there. Yeah. And I was able to tell from the new standard deviation. What would the y bar be? They're saying for a hypothetical, this is right here. This is y bar in the example. But remember, that is not the y bar of this. So when it says this is a hypothetical or the expected sample mean, so that y bar is not the y bar when we do y bar minus mu over sigma over square root of n. That is not this y bar right there, and this y bar are not the same thing. Does that make sense, Kaolin? That's where people get confused, because this top one reads the expected sample mean. This is an observed sample mean. Like, this problem actually gives an observed sample mean down here at the bottom, with the observed sample mean being, it says, like, is it likely that parties will tip on average $15? How much do you expect a party to tip? How much would you expect a party to tip? Do you expect them to tip 15, or how much do you expect them to tip? How much would you expect a party to tip? This might help right here. How much would you expect a party to tip? You'd expect a party to tip how much? How much would you expect a party to tip? Not a salt. Well, how much? On the exact amount, on the exact dollar amount, how much would you expect a party to tip? What is the expected tip of a party? Not 15. Good guesses. So look up here. What is the expected tip of a party? $9. Candido, great job. $9.60 is the expected tip. How much? And then they're saying, what is it likely to observe a tip of this? So they're saying, is it likely that 10 parties will on average tip $15? So that is a mean from 10 parties, making it a y bar. So the mu y bar is the expected mean from 10 parties. The y bar is what we see from 10 parties in observation. Like, is it likely for 10 parties to tip on average $15 when we would expect them to tip $9.60? Does that make sense? It's tough. This is a very conceptual chapter. So it's a tougher one. This is one of the big ones on the exam, or tougher ones. What would the equation look like? I think this one will help. So let's do this one, which is a huge one that catches people. 4 to 53, step 201, chapter 14, homework question 4. Okay, so what do you think we're going to do when we first get to this question? We get to a question like this, and we are going to do what? What do we do when we first get to this question? Yeah, it takes practice. And so here's the thing. You get to a question like this, you do what immediately? What do you do?
Notation, brother.
So you have to practice these steps. You get to a question like this, you say, I need to do this immediately. What do I need to do? Notation. So start telling me notation. Well, we got to do different colors. Tell me notation. I'll take the easy one. Tell me notation. Any notation here? Gotta know the notation. What is the notation? Any notation. Great job, Christopher, right there. That's mu. So that's mu. That's sigma. That's the y bar. So now we have 50 parties. She wants to make 550. Actually, that's not y bar. That's sum of the observations of y. There's no test question that does that. The sum of the observations of what she would get divided by n gets you y bar. So sum of a value, like we add up everyone's money and we divide it by how many people there are. That's the average amount of money. Excuse me. So this would equal to 550 divided by 50. $550 off 50 tables is an average of $11. So y bar equals 11. We don't usually call it SD. It is the standard deviation, where sigma is true standard deviation and S is sample. So this is sample standard deviation from a sample size. It would come from an N, where this is population standard deviation. So good question. there is a such thing as a sample standard deviation. Like if you talk to 10 students and the variation in their data, that would be a sample standard deviation, versus population standard deviation is sigma. So this is considered a truth for a population, so it is sigma. Does that make sense, Kaolin? So when we say SD, I don't like saying SD because you can say the standard deviation of y bar, which is the variation in the sample means, and that's an all right thing to say. But when you talk about variation in data, are you talking about the population's variation or the sample's variation? So the population's variation is sigma, where the sample's standard deviation is S, and then the standard deviation of some characteristic, like a sample mean, is standard deviation of y bar. Does that make sense? So these are all standard deviations. This one on the far left right here stands for the standard deviation of the sample means, which is variation when we collect sample means. This is the population standard deviation, which is if you have all the data, the variation within all the data. And this is sample standard deviation, which is variation within a sample size of like 10 from a population. Are we using quantitative equations or we changed? We're still using quantitative equations because this is TIPS, which is money. So good question. So this question is really tough. And what you need to do is draw it out. If you draw out a distribution, what two quantities do you have to know to be able to draw it? What two quantities do you have to know to draw a distribution? Mean standard deviation. Great job, Braden, right there. So mu y bar equals mu. We already know what mu is. So 10.50, because we already know mu y bar equals mu. So the expected mean is equal to that. The new standard deviation is the original standard deviation of 5.50 over square root of 50, which is going to be like 8.9. So we'll put it over here. It's going to be like something 8.9 or something. So 50 square root, and then 5.50 divided by that, 7.777. And $11 is about here. That's where $11 would be, because this is 1127. Does that make sense how I got 1127? Because the standard deviation, we need a new color for that, or we could use blue. The standard deviation is this metric right here, how much we go up and down each time. And so 11 is less than 1 standard deviation. So does that make sense? 11 was the sample mean. So sample mean was what we were kind of looking for. I'm trying to find a new color, we'll go orange. We got that from the amount of tips you wanted divided by not to find P. This is just one standard deviation above the mean, Christopher. Good question. All I did was find one standard deviation, and then we want to find the amount of times she earns at least $550, which would be this right here. Because $550 is getting an average tip of 11. Does that make sense right here? This part up here where I said she wants to make 550. She has 50 tables. Put it this way. If you have 4 customers walk in and you want to make $100, how much do you have to make on average from each customer? If you have 4 customers walk in and you want to make $100, how much do you have to make on average from each customer? You have 4 customers walk in, you want to make $100, you need to average what with each customer? $25. Yep, at least 25. So she wants to make 550 and she has 50 people walking in. So she needs to average $11. That's what we're doing right there to find out the sample mean she wants to see. And then this is the mean, and this is one standard deviation because the standard deviation is 0.77. So the z-score of this is 0.67 or it's 0.6 something. And I can take a decent guess at this. I'm not going to get it. It'd be shocking if I got it. It'd be amazing. If I got that, that'd be cool. Very hard problem to get if you were to guess it. Sometimes it has easier versions. You have to go to the applet, which is the pinned comment right now. So what we're going to do in the applet is we're going to put in the mean and the standard deviation. And check out, you need to have exactly how I have this. Your mean, your standard deviation, Make sure to copy the true standard deviation we just found, not the true, but the one we found. And then put in your value that you have and go above that. So I was decently close, but there's the exact answer. Let me show you what you need to have in this applet. You need to have find the probability using X. You need to graph above, and then you need to put in the mean and the standard deviation. And Christopher and everyone, does it look like my picture? To some extent, does what I have over there look kind of like what I drew? This is what you want to be able to do if you get really good at this. Does it look kind of like what I drew? I'd say yes. So if you get really good at it, you can draw kind of what you have going on right there, and you'll make a decent drawing. And the answer is 0.2602. And you copy the answer. You go back here. I took a decent guess, not close enough. There's the answer. What do they make on the best 10% of weekends? What's really great is if you've already put your numbers into your applet, you only have to go to find X using p-value. So now we enter in the top 10%. So you already have your numbers entered in with the mean and the standard deviation. Carry all the decimals. Now notice this is her average tip on the top 10% of weekends. Once again, make sure you have find X using p-value, your mean, your standard deviation, your area, and then do the above and 10%, and you should see the top 10% of curve. Now remember, since she worked on 50 tables, what would we do to this number? Since she worked on 50 tables, what would we do with this number? I can take a decent guess once again, but thanks, she worked on 50 tables. So this one, there's ways we can do it on the exam. Got it. I'll show you how I did that. There's ways we can do it, showing you pictures. Check out the exam review, because we show how to do it with pictures when we do it right there. And Noelle said it perfectly, multiply by 50, because you take this, and she worked on 50 tables, and there is right there, and I took a decent guess and got it. But you'd multiply that by 50, because that's her average tip. Tough question, and then we do have ways of doing it. Check out the exam review. Ubot's going to put review 2 in the chat. Woo. All sniffly. I want to be 100% again. Okay. Only 3 more questions. I'm going to try to do it all. I'm going to send an announcement real quick. I'm going to hang out here. We're going to get this whole thing done, I think. The full homework. So I'm sending an announcement. Really quick, I'm going to send an announcement to my class and say, here's the link for class. I'm teaching them on YouTube today, so they don't usually get taught on YouTube. So give me one moment right here. How's everyone doing, though? This is a tougher chapter, I know, hence why I start early, ask questions. But how is that, Logman? How is everyone doing? Would the answer be B? Probably. Yeah. There you go. Because random 10% and large enough n. There we go. Yeah. Random 10% and large enough n. This one's not that bad right here. Random 10%. Seeing a landscape design, so crazy. It's so crazy with it. I'll get this new one going. But yeah, random 10% and large enough n for means, random 10% and success failure for nearly normal. Random 10% success failure for proportions. I'm getting loopy. Okay, let me see right here. Okay. Look up a student. Okay, we're section 01. Okay. I'm sending students in another section, or I'm sending them an announcement saying, here's the link for class. Okay, 1 second. I hate being sick. I ate some soup yesterday. What's a good way? What all classes do you teach? I teach 201, 207, 320, honors 320. I've taught 340. I teach 479 right now, which is the capstone class where you get to learn how to use the tools. It's like basically a class like, which I'm teaching next, like on how do you use everything you've learned. I teach 474, which is data mining. 320 is regression analytics. I teach 475, which is time series. It's about it these days. I think what else I've taught. So I was going to sit outside, but there's going to be a big gathering about parenthood near. What's the big gathering? Parenthood. Hey, DD, good to see you there. What's the parenthood gathering? What's the big gathering? Would the later session be focused on other classes? Oh, it's them? They're out there today? Them? Well, maybe I'll swing by and say hi to them. So let's see what's going on. I'll talk to them. Let's tell them to keep their distance. Ah! Oh, DD, I'm a little bit sick. Not too sick, but a little bit. Huge setup. Yeah, they that is Fletcher. One thing I'll say about, like, no statements of views by Brian Stevens, but you should always be able to talk to people you disagree with. I think I really value civility. I think I have viewpoints as a human being, and you should be able to express your views to somebody and let it be known. And I like talking to people about my views and getting their views and trying to understand them. And I've changed a few minds. I've had my mind changed on a few things. Take care, big hugs. Thank you so much, Didi, right there. So class in 15, completely online. Click the link. Okay, here we go. Click here. I think there is, Christopher. I think thank you so much, Didi. I think there is civility to a certain extent. You'd be shocked. You got in the real world. What people don't understand, I'll say this, and then we'll do this question right here. What people don't understand is you go out, if you went most places and you see what you see on campus where people are like talking and things like that or expressing their viewpoints, a lot of times people will get in fights. People don't understand, like, campus is a place usually where there's a lot of views expressed. And usually, thank you so much, Didi, right there. A lot of times, the majority of the time people just have good conversations. Now, the problem is you get this like skewed view of reality when people show you just the things they want you to see. And I think, I'm going to disagree with people on things. They're going to disagree with me on things. Once again, none of my views are being told right here. My views, Rock knows.
It doesn't matter.
My views are my views. But I think you got to take in those views. That's what we're here to do. And if somebody gives a view that's mean, dangerous, or problematic or things like that, you should be able to express why and how, and they could tell you your views are that, and you could tell them no. You just have a conversation. So I think it's getting good at communicating, and I think you have to have this idea battle, let's say. It's low-key skewed, but again, just my view, I'm chill. Can't put my 2 cents in. Yeah, and sometimes I'll say this too, because, and we might, I don't know if I'll have time to do this question. I'll show you how to do it. I'll do it quickly. I'll show you the speed run of it. This one's not bad. I kind of miss being younger because I was more like on fire with my views. As you get older, your brain, it's crazy. Your brain doesn't fully develop till your late 20s, and it actually controls impulse control. So the parts of your mind that kind of slow you down, that say maybe you should take a breather, aren't in full place till your late 20s. And I kind of miss that younger me. I kind of miss that me that was like, just like you go at it. You just like, yeah, I feel that energy. And now I'm like, let me think this through. Let me be rational. Not that you're not rational, but I definitely did more impulsive things when I was younger. I was more impulsive with how I acted. And it's just different mental, and who's to say that is when your mind is developed? Like it's when your mind is different. Like, why does you are a different person and you act differently. And so I think it's one of those things we have to take into consideration is that, like, you have to learn some impulse control, especially when you're younger, because you're more likely to have it when you're older. But I don't know, then I kind of miss it. Kind of miss being more, kind of miss having stronger emotions. 23, I'd rather to be like feel older. This question, you're setting up the, yeah, exactly. Let's feel Dunning-Kruger. Yeah, Dunning-Kruger is a true thing. So right here, we're going to take the mean, and the mean doesn't change. So here's the mean. The mean doesn't change. The mean is the mean. Christopher's already figuring out. Christopher, we got to throw you big points because Christopher has been solving these out and figuring out how to do all of these. The mean doesn't change. This literally goes to the central limit theorem, and where you have the mean doesn't change. That's not our central limit theorem applet. The mean won't change. The only thing that changes is the standard deviation. The standard deviation gets smaller. So if you take the original standard deviation of 17,616.19 and you divide by the square root of the sample sizes, so 17,616.19, and you're going to have to divide that by the square root of 30, and you could probably just ask your phone. Watch this. Here we go. What is 17,616.19 divided by the square root of 30?
That would be approximately 3,216.2615.
What is 17,616.19 divided by square root of 50?
Approximately 2,491.3054.
This one's really easy because square root of 10 is going to be just moving the decimal. I'm looking down for a moment. I'll look back up in a moment. You're moving the decimal here on this one because it's divided by square root of 10. So I think I did that one properly. Exactly, Steven. Use your phone. What is 17,616.19 divided by square root of 200?
That would be approximately 1,244.9456.
So she get it right. Oh, no. What did I do wrong? What did I do wrong? What did I do wrong? They are getting smaller. The standard deviation is getting smaller. Standard deviation over the square root of n. But I did something wrong. Oh, I think I reversed. Wait, no, that's the mean. That's the standard deviation. Do you see it? Help me out. In my haze. What did I do wrong? If you get one of them wrong, it freaks out. What I can do, let me do this. Let me pull up our studio real quick. Then we have one more question for this. The 800, I think that's like a... I'm pulling up our studio in the background. Then I can cheat even better. Okay. Let me see here. The 800 CEOs is superfluous.
It doesn't matter.
So 17,616.119. Okay, divided by the vector of square root of this vector. And then 30, 50, 100, 200. Okay, there's the answers. Okay. So, no, go away. Unless I'm doing something really wrong on this problem. Here it is. That first one's right. That next one's right. I should have put a round on this. Round to 2 decimals. There we go. So, and it does say 2 decimal places. Okay. So there's the first one. There's the next one. 17,602. Oh, no. Look at this. 1245.65. What did I do? I must have misspoken the phone. There it is. There it is. So if you see right here what I wrote out inside of R to cheat. Last one's wrong. Thank you, Christopher. Good work. And so if you notice right here, you're just taking the original standard deviation, dividing by the square root of each sample size respectively. So I made a vector of sample sizes. So you would just do original standard deviation divided by square root. Does that make sense, Kaolin? It's just you're doing each one or standard deviation divided by square root of 30, standard deviation divided by square root of 50, standard deviation divided by square root of 100, standard deviation divided by square root of 200, and each one it gets respectively smaller. And then this is a simulation. So these values right here, you don't use these values, but they will be theoretically close to the answers because they are close, reasonably close, and also reasonably close because simulations model reality. So the whole point is to show you that the standard deviation gets smaller, the mean stays the same, and a simulation can show you that. The distribution is very clearly right skewed because Monster Man's got a right tail. We cannot not see Monster Man. I'm so sad today. Monster Man. I will never forget you, Monster Man. Oh my gosh, right to the high, left to the low, whatever way the Monster Man's tail goes, that is a right skewed Monster Man. Once again, we have another simulation right here. They're doing the same sort of thing. Notice that the distribution becomes tighter, more normal. But what do you see? This distribution is heavily skewed. So is the n large enough here? Was the n large enough? Yes or no? One of our last questions right here was 6 minutes till Brian's teaching another class. Is the n large enough right here? Is the n large enough? It's actually not. They're being really mean with this last one because if it's super duper skewed, you need even bigger than 100. The test won't do that. It's a mean question. Brock maybe knows. So you're looking at the shapes of these. It is becoming more normal as n increases from a skewed to a more normal with an n of 200. So sometimes when they're super duper skewed, you need even bigger than n of 100. So the simulations do support what the central limit theorem says. The peak of the histogram is the center. The center stays the same because mu by bar equals mu. So the shape becomes more normal and the variability is going to decrease because sigma over square root of n. So it'd be nice, since it's fixing the skew, yep, we just might need a bigger, oh, they don't even, oh, here. Coming on the rule of thumb, with the sample size of 30, the sampling distribution will always be normal. True or false? Just say true or false. With the sample size of at least 30, the sampling distribution will be normal. True or false? Last question, I believe. With the sample size of at least 30, so they don't even get into the big nuances of this. True or false? With a sample size of at least 30, it is false. Don't worry, though. We're going to throw you big 5,000 points. Because remember, the more skewed it is, the larger n needs to be. So if it's super duper skewed, you need a really big n. So because this one's super duper skewed, 30 would not nearly be enough. And you can see it right here with the sample size of 30, not nearly enough. Remember, we look at the shape of it. Great job, Christopher, right there. So depending on the shape, it determines how large of a sample we need. Is 2 going to be large enough right here? Look at the shape to determine, via the large enough n condition, if 2 is large enough. So is 2 large enough such that the distribution of means will be nearly normal? Is 2 large enough? Is 2 large enough? Exactly. It doesn't matter. It's going to be normal. But here, when you get to one that is very skewed, now is 5 going to be large enough? The answer is no. Oh, wow. Look at that. It's amazing what the central limit theorem does. You sometimes are shocked what is large enough because apparently 5 is large enough. So 5 was large enough there and kind of large enough here. So 30 is not large enough because it's heavily skewed. Due to the extreme right skew, you can see in the simulations that 30 was not large enough. This is an extremely right skewed data set, so it probably requires a very large n. More skewed, larger n. So the answer is going to be, since the distribution for the simulations, they do become more normal, it does not hold. Since the distribution of means for the sample remains skewed, the rule of thumb does not hold. It doesn't get large enough such that it is nearly normal. So that's got it. I should put a note when the last question was. Big office hours. Big office hours here. This is a tougher chapter. Stat 201. Chapter 14. Homework. Question 7. We'll be back later. I might go see those people. Say hi to them. Say hello. Hello, Fletcher. Why didn't you tell me you were here today? Thank you so much. Need some Red Bull or Weeble? Oh, Weibull distribution. The Weibull distribution. That's good stuff. Everyone give some W's for Didi in the chat. I'm always glad when Didi's here. Visitor from all the way over in Germany right now. Type of a stats day. So give some W's for Didi. And we're going to throw 1,000 points. Always good seeing friends and students here. So keeping me positive, giving me energy. WDD right there. So the Weibull distribution is a totally different distribution. So thank you, Kaolin. Thank you, Noel. Thank you, Christopher. Thank you, Candido. And you're welcome. So with that, we'll head on out and we'll do an outro. Outro time!
Hey Brian, what's up?
Hey, Adam.
Oh, what's this?
Adam, what are you doing? Adam!
No!